So here we're going to use this diagram from Dexter Perkins' online mineralogy textbook here to explain polarized light in a petrographic microscope. Now what he's showing here is that we have a light source. Well, the light source is really out of the field of view, but that would be a light bulb at the bottom of your microscope. And he's showing light vibrating in two directions, kind of an east-west direction here in green and a north-south direction in red. But in reality, of course, the light can move in any direction, as he very nicely explains in his figure. So you can imagine light vibrating in all possible directions as it moves upwards in the sense of this diagram here. So it's vibrating in all these planes. Then we have this bit of polarizing film. This is what we call the lower polarizer, or sometimes the lower nickel, Nicol, and that's in honor of a French fellow, Nicol, who developed this method of microscopy. So notice that the way that the Nicol is illustrated here, it only passes light relative to our view here that vibrates in a north-south direction. So all of these vibrations are being blocked except for one, and that's this one that is vibrating here in the north-south direction, that red beam, the red component of the beam that's shown here. The green is blocked, and so would any other ray vibrating in any other direction. That means, of course, when we look at the light up here, it will be not just polarized, but also darkened a little bit. We're losing some of the total light that's passing through that filter. Because all of the light vibrates in a plane, we call it plane polarized light. And we write it P-L-A-N-E, not P-L-A-I-N, because there's nothing plane in that second sense about it. Plane here means that it is polarized, so it vibrates in a single plane. And if we have plane polarized light, then we can abbreviate that as PPL. Now you might imagine that we could place a mineral. So let's say we have a thin section of a mineral, and that mineral is just sitting here in some green box there. And so let's just draw that green box right here. And that green box, that would represent our thin section. And let's say inside of that thin section there is some kind of mineral that is sitting in the center. But we'll just imagine a very, very large mineral grain. Now the light that is passing through the edges of this material that doesn't hit the grain will be vibrating in a north-south direction as it's shown here. But once that light hits the mineral itself, many minerals, not all of them, things that are isotropic will have no effect, but anything else, any other kind of mineral that's not in the cubic system will take that light and bend it so it moves in some other direction. So the vibration direction will be changed once it hits that mineralogical material and passes through. So there's yet another kind of polarization. There's this original polarization from the nickel here, but the mineral itself is also causing a type of polarization where it takes some of this north-south vibrating light and then bends it in some way. Well, you can imagine that up at the top of the microscope, we might insert another polarizing filter. So we'll just make a copy of this fellow here. Just imagine that we've got another filter up here, but instead of having north-south light being passing through this filter, we'll make the vibration directions east-west. So here's an upper polar, we'll call it an upper nickel, just to use our other terminology. So the upper nickel here only passes east-west light. Now, if you take the mineral away, if this lower nickel only passes north-south light and the upper nickel passes only east-west, then all the light would be blocked and nothing would come through. But if we had this mineral grain set here on top of the stage, so it passes stuff that's vibrating, let's say, in this direction, that mineral, we could do a little bit of vector analysis, will have a little bit of an east-west component to it. So we could take this fellow and break it up into a north-south component and an east-west component here. And it's that east-west component that will be passed by the upper nickel. When we have two nickels or two polarizing filters in place, then we call the system as being crossed polars, or sometimes we could just abbreviate it as XPL for cross polarization. That means we've taken two polarizing filters and put them at crosswise orientations relative to one another They would ordinarily block all the light if there was nothing here. You take this green material here, which we could barely see, pull it off the stage, all the light would be blocked. This lower nickel would only pass north-south, this guy would only pass east-west, and so what we would see would be dark. But when we put a mineral here, we place a mineral that takes that north-south light and bends it to some angle, now there will be an east-west component that will pass through that light, through that upper filter, and that's what we would refer to as the cross-polars view of that mineral. So in a petrographic microscope, we have a lower nickel, and then an upper nickel, and then we have what's cross-polars, or sometimes referred to also as cross-nickels. This lower nickel is always in place. That's a permanent feature of the microscope. This upper nickel you can place in the direction of the field of view, or you can pull it out and remove it so you don't see its effects. So that's a choice we can make whether we want to view plain polarized light, which means that the upper nickel is out, or whether we want cross polars, which means that the upper nickel is in.